All right, we should start. Down to 3 of us, just like that, week 4. Dropping like flies. It's not good. All right, 24 and 25 was your homework due today, correct? Yeah. And then you have 26 and 33 due Wednesday, so. We have an exam on the 9th, 2 weeks. We'll have another little quiz on Friday. And we just keep rolling along. So we'll try and get through chapter 4 comfortably for the exam. Probably not much into chapter 5. This next week, the quiz is in class, yeah. It's Friday, and it'll be over this chapter. Chapter 3, maybe a simple one out of chapter 4. Maybe. All right, let's go over the homework. Grind on this a little bit. 24 said compute the moment. Your shadow. I think somebody asked me last time, what's a kip? Yeah, 1,000 pounds. Kip's 1,000 pounds. So a ton, most of us know that one. Whoa. Ton is 2,000. A kip is 1,000. And we really just use it to make big numbers smaller. That's it. So it didn't tell us like how to do this one. There's 2 ways to calculate the moment from a force. You can do it by the formula directly. And if you do it that way, the distance you put in has to be the perpendicular distance. So on this one, if we did it by the formula directly, we'd have to extend the line of action of the force. Oh, it's not automatically extending or duplicating. Thanks. That's important. I don't know why. I think ever since I lost the whole system off the table. It's good. Yeah. All right, so extending the line of action. If you're going to use the formula directly, that's got to be the perpendicular distance. It's not 3 feet. That's not perpendicular to the 2K. Perpendicular is like out here somewhere. Which this one's not that difficult. Like probably could do it this way, no problem. So if this is 70, right, and this is a straight line, then that right there is also 70. And we know the hypotenuse is 3 feet, so we could probably calculate this distance. There's trigonometry skills. I'll say sine 70 equals opposite distance perpendicular over hypotenuse 3 feet. So the distance perpendicular is 2.819. 0.819 feet. You didn't have to do it this way, but I just want to show how to use that formula directly. So then the moment would be force 2K times 2.819 feet. That's the moment at A. .64. That's a kip foot. It's not a kip per foot. It's a kip foot. We're multiplying kips times feet. Rotation If I think about attaching a string, it's going to rotate that way. That's clockwise, so that's negative. You can just call the rotation. You don't have to make it negative. Yeah, as long as that's there.
I put like an arrow.
Yeah, that's fine. So the other way to do it was the other method that we talked about, which is the component method. So I want to do it that way also. So when you do the component method, you're going to put in the components, X and Y, and then you just find the moment of each one of these, right? Really the Y comes right out of here, but you got to build a triangle to find these things, right? So this is Fy of the two. This would be Fx of the two. So the component method says, put the components in, take the force out. So we're going to take the 2K out. We're going to put these two components in, and then we can calculate the moment of each of those. So what about this X component? What's the moment of it about point A? Remember, if the force goes straight through the point, does it create a moment? Does not. So if you do the component method, most of the time, not always, most of the time, one of the vectors, one of the components will just drop out of the equation. So this X component does not create moment about this point. So we don't have to deal with it. All of the moment is created by this component, Fy. So I do need to do that one. So I'll find out what this is by doing the sine of 70 opposite Fy of the 2 over 2K. So I'm just finding that component based on this triangle. So the Y component of the 2K is going to be 18794. 18794 K, because that's a component, that's this component. And then the moment about point A, since this X drops out, we just deal with the Y, and now we have a nice clean 3 feet for the Y. So it's 1.8794 K times 3 feet. And hopefully it's exactly the same as this, and it is. The two numbers are actually exactly the same out there. Several places, 5.64. And same rotation. So you can do components, or you can do the equation directly. The equation directly, just make sure you're using this perpendicular distance times the 2. If you're doing components, put the components in, think about which one drops out if one does. This one dropped out because it goes straight through the point. All the moment is created by this Y force. So 2 different ways, same solution. Questions? It's good. Yoke. 25. I think the same statement, right? Compute the moment of the force about point A for the conditions shown. Not a great drawing. So the only thing you can do with these kind of drawings is just kind of make some assumptions. This 5 feet is given to this edge right here. We're not given the thickness of this thing, so we can't really do anything about that. And then this looks like it's from like the midline, like where this is, down to the bottom. So A really must be right there. It has to be. If it's somewhere else, then we really don't know the distance of things, right? So you just kind of gotta go with what they give you to calculate the moment. You gotta kind of locate where you want that moment. Anyway, it's gotta be here because that's where the dimensions run to and from. All right. Sorry about that bad drawing. But same way, we can do this by the definition. If we can figure out the perpendicular distance. Did anyone do it this way? Like, where is it? It's like right in here somewhere. That's the perpendicular distance from the force to the spot. So if I'm gonna use M equals F, I have to find this. That way one? No. Gina, did you do it that way? Yeah, I wouldn't do it this way. I would do components. So. I think you could do it, right? You'd have to build a triangle like this. And then you'd have to calculate this based on those two, so that wouldn't be that bad. The 60, yeah, it just looks difficult. So I wouldn't do it. I do components. Right? Because our new theorem says, hey, we can use the components instead of the force. So that's our Fy. And this is our Fx. And if I think about the moment of the Fy, that's pretty easy. It's just times 5. And the Fx is times 20. So those perpendicular distances are a lot easier if I can find Fx and Fy. I'd probably put Fy over here to find it using the 60 degrees. That's going to be sine is opposite. That's the Fy over 150. $29,903.8. And that is pounds. That is going down. Right, that's just working this triangle here. And then X would be cosine. $75. So once you get the components, then you can find the moments of the individual components. So if I'm doing the moment at A, I'll do the Fx force first. Magnitude of the X is 75 pounds. The perpendicular distance, we have to think about where X is. It's along this line of action right there. And the perpendicular distance is 20. $1,500. And what's the rotation? How does it rotate about point A? Fx. Here's my point, here's my force I'm thinking about, that one. Yeah, it's gonna go like that. Counterclockwise. So that is positive. We need those directions. Because we're gonna add these moments up. If you have multiple vectors, doing individual moments, you gotta add them up. Moment at A of the Fy force is going to be the 129. 9038 pounds. That's this one, right? The vertical one. So if I think about its line of action right here, and the perpendicular distance is right here. Making 90 degrees, that's 5 feet. $649.5190 5 foot pounds. And the Y rotation is it's gonna come down, it's gonna rotate around that way. Also counterclockwise, positive. So in this case, the X component and the Y component are creating the same effect. Both of them positive rotations, counterclockwise. That means when we add them up, moment a day, we just can add these. They're both positive. Total moment a day is gonna be plus 2149.519 foot-pounds. Counterclockwise, positive. So it's at point A, 2149. A little too much around, or a little too much accuracy there. 52 foot-pounds, positive rotation. We have to have this skill set down to do non-concurrent force systems, so. Questions? So quiet in here. Either like have this dialed in or you don't have a clue, one or the other. But gotta ask questions if you're lost, that's all. You don't know what I'm doing, that's not good. All this kind of stuff will be on the exam in 2 weeks, so you want to dial it in best you can, practice it as much as you can. So that was the component method. We took the 150, got rid of it, put in X and Y, and then found the moment of X and Y. All right. Just 2, right? Turn them in. I'll take them. We will move forward. We can just pile them over there. We're gonna do number 29. Pretty sure that one's not assigned, just as a practice. More practice than these non-concurrent. So non-concurrent parallel. All the forces do not go through the same spot. Four feet. 3 feet to there. 2 feet to there. No distance in the end. 2 kips. 5 kips. 4 kips. There's a support here. Something like that. I give you a bit to draw it. And what they say for this whole kind of set is, ooh, this is resultants. Yeah, this will be good. They call that point A. All right, this is going to be a lot, but I'll show you how we do it. It'll be a good first run. So 4 feet is all the way from force to force. Where's Evan? Oh, Evan, hang in there, man. Week 4, 5, and 6 are the hardest, just saying. We get the midterm low energy week 4.
This is me.
And it's the 4, 5, 6 is midterm, right? Week 4, 5, and 6, super hard for students. You're feeling the effects of all your courses. You're feeling the effects of winter. You're feeling the effects of everything. Super hard to stay focused in 4, 5, and 6. All right, so this problem says find the resultant. So let's remind ourselves of what the resultant is. So the 2 force systems that we're working with, the 2 different kinds are this kind. Remember what these are called? Yep, concurrent. So we did this. We took all of these and turned it into the one force, the resultant, right? That's what the resultant is. It's the one force that can get rid of all of these. So here's my point A, and now I have point A. So when we say find the resultant, we're looking at the single force that is the replacement for these 3. And that was concurrent. Well, this is definitely not concurrent. It's non-concurrent, right? All the forces don't act at the same spot. So we need different strategies than this. That's why we did the moment thing. When forces are a distance apart, they create rotation. So we had to have this moment thing, and I'll show you why. But if they want to know the resultant of the parallel force system shown, locate the resultant in respect to point A. So if they tell you where to find the resultant at or where to locate it, then that's where we're gonna do our moments. Because basically we have to take these three forces and move them to point A. Okay, well, we can't just move forces around, that's not legal. So we have to figure out a way to do it. So we have to move all the translational effect, the up and down effect, or the side to side effect, and we have to move the rotation. If we do that, then we've captured the full effect of the force. So really what we do is we take the 4K and we literally move it over to A. 4K. That keeps the translational effect of the 4,000, right? Still trying to push up that amount. But now I need to bring the moment with it. So I took this and moved it over here, but now this was creating a moment about point A, right? And we've done these, we've practiced making them. So I have to calculate that. Moment of A of the 4K is 4,000 or 4K times what? Perpendicular distance. What is that? 7, yep. 7 feet. Again, parallel systems are the easiest. Like the distances are nice and clean. We can see it. How far is it from 4K to A? It's 7 feet. What's that number? 7 times 4 is 28. Kip feet, not kip per feet, but multiplying those. And what's that rotation? I already drew it up above, but it is clockwise, negative. So once you do that, you put it in. Graphically, we can put it in with a rotation arrow, that stands for moment, and then 28. Kip feet. So this is called a force moment. That's how we move the 4K over to A. We move the force and we bring the moment with it. It makes sense? Kinda? All right, got to do all of them. So now I'm going to bring the 5K over. You can draw it however you want. I just put it up here, 5K. So now I've moved the 5K over and I have to bring its moment with it. Moment at A of the 5K is equal to 5K times what? How far is it from 5K? Yep, 3 feet. 15 kip feet. And what's its rotation? About point A. Yeah, it's gonna go like this. So it's like this, which is positive. And we need to draw it in. I just loop it around the top. It's gonna get busy. But now the 5K is moved. I brought over the translational effect, the up and down effect, by writing 5K and a vector. And then I brought over the rotation effect, 5K times 3. We have now the 2K to do. I'm out of colors. I'll go back to red. Moment of the 2K about point A equals 2K times what? 2 feet. We're starting to get the rhythm of this. Equals 4 kip feet. And its rotation looks to be clockwise or counterclockwise? Clockwise, negative. Not gonna draw that one in, so it's just getting busy. But just for kind of demonstration purposes, I'm gonna show you what we have now. So here's my same beam. Here's this piece right here. Here's my point A. Here's my roller. I've got 4K, 5K, 2K, because I moved that one over here too. I should draw it. Put it down here. 2K. All right, so all the vectors have been moved over. And all their rotations have been moved over. So we have the 28. The 15. And the 4K. 4K feet. 3 vectors, 3 moments, all moved to point A. And we can do that because we took the translation effect and we took the rotational effect. All of that's legal. All of this is exactly the same as the original forces. The effects are the same for statics. We're going to see how we did that. So then we just add things up. I'm just going to keep redrawing the beam. You don't necessarily have to do that on your homework, but it's handy to teach it. So 2K down, 5K down, that's 7 down, 4 up. We have a resultant of, kind of made that a little close. What, 3? 3K down. Right? We got 5 down, 2 down, that's 7 down, 4 up. The difference is 3 down. And we do the same thing with the moments. We have a -4 and a -28. That's -32. And then we have a +15. Gives me a -17. All at point A. This is the answer. The resultant would be 3K. It's at point A. And it has a -17 kip feet rotation. So it is a force and a moment at A. Sometimes we don't have a specific point, we just want to know where the resultant is. So that's a little different problem, but this is the first crack at finding the resultant of a non-concurrent. So we started with 4K here, 5K here, 2K over here. We wanted to know, like, what does A feel? And A feels this, 3K down and a rotational effect. So what's a rotational effect due to a beam? Anyone have any idea? So here's my beam again. It does have supports. I didn't draw them in there. But remember, it had a little triangle here. And it has a little round thing here, right? And then point A was in here somewhere. And point A is this 3K in this moment, right? So rotational effect means that the inner fibers of the beam feel some kind of a rotation. So if there's 3K, I'll write it actually what it is, 3,000 pounds here, pushing down. What's this whole beam feel? This whole beam feels this. Doesn't it? Put a bunch of weight between two supports, it's gonna bend. So that bending, that's what creates this moment is what creates that bending effect. It's literally trying to rotate the whole beam, right? So super important that we know what this number is, the 17 tip feet, because then we'll be able to calculate how much bending and deflection is going on in this beam. That's very important. Bending and deflection is what fails things in this country, not braking. We don't really deal with that braking effect. We deal with deflection. So if you walk across a floor in a home and it bounces, you know, it's like springy, that's failure. We don't want that to happen. You want to walk across floors, structures, like if you're walking on the upper level, you don't want the floor like going like this as you walk across. So deflection is one of our huge constraint. You don't want to drive across a bridge and see the bridge going like this. It's not what you want. It's not a comfortable feel. All right, good job. Let's take a break. And then we'll do a little bit more. So another find the resultant. When they say with respect to A, that is where typically you're going to collect your forces. So non-concurrent system means we have to use moments. When we did concurrent systems, we did not do moments. No moments, because all the forces are here at one spot. And we're going to collect them here, and we're going to get our force here. Goes right through the point. There's no moments, no rotation, right? On the whole concurrent thing. Non-concurrent, you've got to use moments because you're moving forces from location to location. So you're going to move everything to A. The 40 is already at A. So we don't have to move it. It's already here. So don't worry about that one. But the 20, we got to move over. So it's going to come over here. What's the unit on this thing? Like pounds? Yeah, everything's in pounds. So move it over and then bring the moment. How much is the moment of this 20-pound force? About point A. 2 times 20 is 40, right? So this is the translation, but this right here is 40 foot-pounds. So bring the vector over, bring the moment with it. Then we got to bring this 20 over. So that's another 20 pounds. And another rotation. Those are both clockwise rotations. Just got to keep track of which way they go. And this one's 20 times 10. So this is a bigger one. Gets really busy, so I just put it up here. 200 foot-pounds. 20 times 10. So here's the force. I brought it over. Here's its moment. brought it over. Now I need the 80. So another 80 pounds. And its rotation. That's this way, right? Goes up and around, so it comes around counterclockwise. 80 times 12. 960? Yep, 960. So that's the way you move vectors. Gotta have its translational effect and its moment. So now my beam looks like this. I'm gonna sum them all up. Here's my point A. Adding all the vectors up, 20 down, 40 up, 80 up. Looks like it's 80 up. Adding up all the moments. We have 20 going clockwise, we have 200 going clockwise, and we have 960 counterclockwise. So I'm actually gonna just do that. So remember, clockwise is negative. So that's a negative 220. And then we have a big positive. 960, so. It's like 740. Everyone see where I'm getting these numbers? All right, just add the moments. Add the vectors. It's so easy when it's parallel. It gets so much harder when these things are not parallel. But we'll just ride this easy way for right now. Now, the last step, we didn't do it on this one. This one, I just left it here, right? At 3K and 17 kip feet. So what we typically do is we now distribute the resultant out onto the beam. This is the resultant magnitude, 80. So if the problem is just asking for the resultant magnitude and that's it, R equals 80 pounds. But R is actually out on the beam somewhere. If there's a moment with the force, then there's some rotational effect left over, right? If there's no moment and we just have the resultant, then we're clean. We know where the resultant is. So the last step is to distribute the 80 out onto the beam. In other words, it's really out here somewhere. I don't know where, but this moment is going to tell me where. It's going to help me. Because what's a moment equal? Force times distance, right? Yeah. And what's my moment? 740. And what's my force? 80. And what's my perpendicular distance? I don't know. In other words, I don't know where the resultant is. It's out on the beam somewhere. I know the resultant moment is 740. I know the resultant magnitude vector is 80. So I can put them into this equation and determine where this resultant is. 740 divided by 80. 9.25 feet. Okay. Now, it's got to be out here. It's got to point up just like that. That is the resultant, but it's out here somewhere at 9.25 feet. I know it's out here. 9.25 feet. And it is 80 pounds. Because that would create the same rotation as this. In other words, out here, about point A, it's going to be this same kind of rotation. So that's how I know it moves to the right and not to the left. There's no beam over here, so it kind of makes sense it moves right. But we can get resultants that are actually off of the beam because it is just an effect. It's the resultant effect. These are the vectors on the system, and this is just what the system is feeling. So when we put it out here, 80 pounds, then we know exactly where the resultant is. And its magnitude. The resultant is 80 pounds and it's 9.25 feet from point A. So R equals 80 pounds, 9.25 feet right of A. Non-concurrent systems. Collect everything at one spot, add it all up, redistribute the resultant back out onto the system. Now, good? It's a lot. Take some practice. You'll get one practice problem like this. But the practice problem you're gonna get has a distributed load on it. So we should talk about distributed loads and how we deal with them. Distributed load looks like this instead of a concentration. So I'm gonna say this is 8 feet. And we'll put another force out here. That's a concentration. We've been dealing with that. 200 newtons. And then the way these are called out is 100 newtons per meter. So the book will call these things out, and that is per meter. Like here, this is 1 kip per foot. This is 2 kips per foot. This is 200 pounds per foot. So it's telling you for every foot we have this weight, right? It's a distribution. And I'll give ourselves some distances here. And I'll call this point A. So this problem might say find the resultant with respect to point A. Same kind of problem. We got to find the resultant. We got to move everything to A, right? Well, we know how to do it when our concentrations are here, like this 200, right? We just move it over. 200 newtons. And then we find the moment. It's going to create a moment like that, and it's going to be 200 times 4. 800 Newton meters. Right? That's how we move vectors. But when you have a distribution, it's a little different, of course. A distribution means we have like a pile of something, right? Pile of plywood, pile of dirt, pile of snow, something that's covering an area. So for every meter, sorry, I have crossed my units. That's not going to work. These are all meters. For every meter, we have 100 newtons. Okay. So the way to get the concentration of a distribution is to calculate the area. The area of a rectangle, since the 100 newtons refers to the height, the 8 meters refers to the length, we could just calculate the area of this distribution. It's gonna be 8 meters times 100 Newton per meter. And that's gonna equal 800, right? And then what happens to the meters? They cross out, we're left with newtons. So to get the concentration of a distribution, you just calculate the area of the distribution. So we know it's 800 newtons. Where do we put that? You put it through the geometric center of the distribution. What's the geometric center of a rectangle? Halfway. Yeah, so it goes here. Halfway, 800 newtons. Now you treat this just like you treated the 200 or any other concentration. You move it. So move the 800 over here. Calculate its moment. It's here though. It's not over here or here. It's right here. This is 4 meters. This is 8 meters. This is 4 meters. So it's 8 and 4, that's 12, and another 4, that's 16 meters to this 800. So 16, 800 times 12,800. Newton meters. So the way to deal with distributions is to concentrate them. Calculate their area. Put the concentration through the geometric center. So if you have a triangular distribution, you have to calculate the area of a triangle. And then you have to put the concentration through the geometric center. So if you don't know the area of a triangle, the front of the book has that. Areas of shapes. That's why that's here. And then also where the geometric center is in the front of the book. So we're gonna do triangles. Rectangles are easy. That's the one we just did. It's halfway. But we're gonna do parabolic curves. Both concave up and concave down for loads. So it gets complicated. We have to be able to concentrate these distributions. All right. So now we've got it all over here, just like we did before. And now it's the same as we've done. We just add this up. So here's my point A. We've got 800 down, 200 down. So that means we have 1,000 newtons down. These are also additive. So our moments can become 12,800 plus 800. 13,600 Newton meters. And then, of course, we'd want to know where this 1,000 newtons, that's our resultant right here, where it is on the beam. So here's the beam. It's going to go out here somewhere, 1,000 newtons at some distance, but I don't know how far. I have to use my moment equation to calculate that. So this is the moment. So the 13,600 Newton meters equals force 1,000 newtons times the perpendicular distance. Just move your decimal 3 places and it is 13.6 meters. Whew, it's a lot. It's a lot. We took a distribution and got rid of it. Turned it into an 800 concentration, then moved it all to A, then added it all up at A, and then redistributed it back out onto the structure, the beam, whatever the heck it is, right? So then the solution's gonna look something like, you don't have to draw it out, but I tend to draw it out. Right, 1,000 newtons, 13.6 meters from A. Non-concurrent, find the resultant. That's what this is. All right, you have a couple problems to do. One of them is like that, right? I think you're doing 26, correct? Yeah, 26 is this creature. And it says find the resultant with respect to A. So you're gonna move all these over here, move it back out. And then 33 is this thing with a couple distributions. So again, find the resultant and where it's at on the beam. Concentrate this, and then go to work on it. So. And we'll do more on Wednesday. Good job. Stick to it. It's a lot. You have to fight your way through it.
So for 33, it says compute magnitude and location.
Yep.
Result.
Yep. 33.
Yeah, definitely. And you get 2A, so.
Yeah, so this is kind of where we're heading, where you just get to choose, right? They only give you A, but you could label this B, and you could do it. You can do it anywhere. They're not telling you where, so I would just do today. Bring everything to A. Just keep it simple for now. But in the future, like these more complicated problems, and you'll notice chapter 3 has a pile of practice problems. It's a big chapter, like conceptually, if you don't get chapter 3, you'll never get chapter 4 or 5. You just won't get it. So you got to make sure you get this down. But there's just a lot of problems. And these are not going to say, like this one does, this one says do it at B, but still, we're going to end up doing these wherever we choose, right? We get to pick, so. They don't tell you, then you get to choose.